Hello, my name is Saurabh Kadekodi, and I'm here to talk about Pacemaker, avoiding heart attacks in storage clusters with disk adaptive redundancy. This work is meant for large-scale storage clusters. To give some context, large-scale storage clusters today have thousands to even millions of disks in their primary storage tier. At such scales, disk failures are very common. Disk failures are measured using a metric called annualized failure rates, or AFR, which is nothing but the expected percentage of disk failures in a typical year. To protect against data loss in the face of disk failures, the commonly used technique is data redundancy. You might be aware of commonly used redundancy mechanisms such as replication or erasure coding. For example, here I've shown a 6 of 9 erasure code where we have 6 data chunks and 3 parity chunks to form a stripe. Multiple redundancy schemes may be used together in a disk fleet, but the redundancy schemes are unaware of the AFR differences on which the data is stored. This is a problem because today's clusters are made up of a mix of makes and models, and they have different failure rates compared to each other. This results in different levels of data reliability given the same redundancy scheme. For example, here I've shown two 6 of 9 stripes, and the top stripe has 5 chunks stored on purple disks, whereas the bottom stripe has only one of the chunks stored on purple disk. If the purple disk AFR is much higher compared to the blue or the green disks, the data reliability provided by the top stripe is much lower compared to the bottom stripe. Moreover, if the redundancy scheme has been decided based on the AFR of the purple disk, then the bottom stripe is overprotecting its data. Whereas if the redundancy scheme has been designed using the failure rate of blue or the green disks, then the top stripe has its data under-reliable and is at a risk of data loss. Thus, the same level of redundancy is either insufficient or overly wasteful, and both are bad. Now let's take a look at how different the AFRs actually are across the different makes and models. In this work, we analyze over 5.3 million disks spanning 60 makes and models across 3 production environments at NetApp, Google, and Backblaze. In this plot, the left axis is AFR, which is plotted on a log scale, and each box has disks belonging to a particular make model and the AFR spread in those disks. And the takeaway from this slide is that there is over an order of magnitude difference between the strongest and the weakest disk. To make matters even more complicated, for disks belonging to each make model, they have an AFR distribution over its lifetime that also changes as the disk ages. The disk AFR lifetime distribution is denoted using the disk hazard curve, or also colloquially known as the bathtub curve. The bathtub curve has the age of the disk on the x-axis and the AFR on the y-axis. When disks are newly deployed, they are in their infancy and they have a high failure rate, which is often referred to as infant mortality or burn-in. This is followed by a low, stable failure rate regime called useful life. And finally, when the disks are old, the failure rate increases again in what is termed as its wear out. So the disk failure rate changes across makes models and over the disk's lifetime. The concept of disk adaptive redundancy is the following. In a cluster that does not support disk adaptive redundancy, no matter how the failure rate changes, the redundancy scheme once chosen for a disk remains constant throughout its life. And so the AFR range covered by the reliability remains the same, despite the underlying AFR curve going through different changes. In disk adaptive redundancy, the redundancy is dynamically tailored according to the changing failure rate. The key advantage of this mechanism is that by lowering redundancy during the low AFR regimes of a disk life, it results in lower storage cost. The heterogeneity-aware redundancy tuner, or HeART, was the first system to propose disk adaptive redundancy. This work has been published in FAST 2019. HeART simulated disk adaptive redundancy on a storage cluster that had over 100,000 disks, and it promised substantial space savings over the one scheme fits all redundancy approaches. Specifically, it promised over 33% lesser space required over 3-way replication, and even on the space optimized redundancy schemes, such as 6 of 9 and 10 of 14, it promised space savings of 11 to 16%. In today's storage clusters, any space savings over 10% translates to tens of thousands of fewer disks that are required. So disk adaptive redundancy has a real potential to reduce storage and energy costs. Looking at these numbers, all clusters should right away be using disk adaptive redundancy all the time, correct? Unfortunately, disk adaptive redundancy today faces a fundamental problem, and that problem is transition overload. To explain transition overload, I'll bring back the bathtub curve of disk adaptive redundancy. So these steps that you observe in the gray patch are actually redundancy re-encoding or transitioning whenever redundancy is re-encoded or transitioned. Each one of those redundancy transitions comes with a high I/O cost of re-encoding. That is, redundancy transitions are not for free. Secondly, when the AFR rises towards the later half of the disk's life, all those transitions are urgent, meaning that they cannot be arbitrarily rate limited, because doing so might make the AFR go beyond the tolerable limit of the reduced redundancy's AFR tolerance. And that might render the data under-reliable. So the combination of high I/O cost combined with urgent transitions is what we term as transition overload. And transition overload is a showstopper for today's systems. To look at how bad transition overload can really get, we simulate existing disk adaptive redundancy systems on some clusters that we evaluated. In this plot, we have a cluster's disks deployed in a cluster over its lifetime. The x-axis is the calendar date, and on the very left is when the cluster was born, and over time disks have been deployed into the cluster. The right y-axis shows the total number of disks running in the cluster on any given date, and at its peak, this cluster had over 350,000 disks. Transition overload when HeART was simulated on this cluster is what is shown on the bottom plot. The left y-axis is the total percentage of cluster I/O bandwidth that is spent only in redundancy transitions. The x-axis is the same as the top graph's x-axis. And so I'm going to be combining these plots henceforth like so. And what we observe is these black patches, which are essentially the transition overload showing up. In fact, it can get so bad that around 2019 September, we can see that for weeks at end, all that the cluster is doing 100% of the time is redundancy re-encodings. And this is owing to the costly I/O of re-encoding and too many disks transitioning together. Now, this bad level of transition overload was not just an artifact of this one cluster that we evaluated, which was a Google cluster. We also evaluated 3 other clusters, 2 of which belong to Google, and one of them to Backblaze, the backup service. And in all clusters, we see that transition overload is predominant and essentially renders disk adaptive redundancy useless as it stands today. Pacemaker, our system, is designed to overcome transition overload. Pacemaker is designed around 3 crucial questions. When should disks transition? Which redundancy schemes should disks transition to? And how should the disks transition? This is Pacemaker's architecture diagram. And I'll go over the components of Pacemaker in the context of these questions. So first is the proactive transition initiator, which helps Pacemaker anticipate a change in AFR soon enough such that the transitions can be issued proactively and can be safely rate limited without risking any kind of data loss. The next is an R group planner, which has a constraint-driven approach, and storage administrators can essentially define a constraint on the amount of I/O that they're willing to spend for redundancy transitions. And the R group planner intelligently chooses the redundancy scheme to transition to such that these I/O constraints are maintained. Finally, Pacemaker also has 2 new I/O efficient transitioning mechanisms that allow it to reduce the cost of I/O transitions by having through these mechanisms. So let's first look at the proactive transition initiator. But before I go into the details of that, I'll first talk about 2 important disk deployment patterns and their effects on Pacemaker. So the first important disk deployment pattern that we observe is something we call trickle deployments. This is when disks are deployed a few at a time, but regularly. So tens or hundreds of disks are deployed every so often. This results in a gradual increase in the number of disks deployed in the cluster. In contrast, we see step deployments where tens of thousands of disks are deployed very close in time, say a fortnight. And then for months together, there are no new disk deployments. Each one of these disk deployment patterns pose different challenges for disk adaptive redundancy, and Pacemaker tailors its approach based on the disk deployment pattern. So first, let's look at proactive transition initiator in the context of trickle deployments. Now, trickle deployed disks are deployed regularly, but a few at a time. Nevertheless, in order to get statistically accurate AFR estimates to understand when to change the redundancy, Pacemaker has to observe at least a few thousand disks at a given age. Now, because disks are deployed a few at a time, by the time Pacemaker is confident about the AFR for a given age, the oldest disks are potentially months older, and the data has been under-reliable for a few months. That could be dangerous. To overcome that, Pacemaker has the concept of canary disks. So Pacemaker marks the first few thousand disks, in this case 3,000 by default, as canary disks. And Pacemaker only learns the AFR curve from these canary disks without optimizing the redundancy for them. So canary disks are always protected with the highest level of redundancy that's possible. By understanding the inflection points of the AFR curve and the ages at which the transitions are required, Pacemaker then applies this knowledge to the bulk of the disks that follow from behind and proactively transitions those disks such that they can be safely rate limited. For step deployed disks, Pacemaker has a different approach. So unlike trickle deployed disks, step deployed disks are deployed a few thousand at a time. The canary disk logic cannot be used for step deployed disks because most or all of the disks are deployed together. And if we were to treat all of them as canaries, essentially there would be no disks left over or very few left over to make it not worth all the redundancy transitioning effort for the space benefits that we will achieve. Therefore, Pacemaker instead leverages the fact that step deployed disks have a few thousand disks that are of a certain age on a certain date, which is not true of trickle deployed disks. And therefore, those few thousand disks that are aging together can provide high confidence AFR estimates from the get-go. Moreover, disk reliability analysis that we have done as a part of this work also points to an important fact that disk AFR rises gradually and not suddenly. So combining gradually rising disk AFRs along with high confidence AFR estimates, Pacemaker has devised an early warning system for the rising AFR in the context of step deployed disks. So what that means is when the step deployed disk's AFR crosses a certain configured threshold, Pacemaker knows that the AFR is going to rise in the near future, and it proactively issues the transitions such that the transitions are rate limited but can still happen before the AFR crosses the tolerable limit of that redundancy scheme. Now let's look at the IO efficient transitioning mechanisms that Pacemaker has invented. I won't have time to go into the detail of our group planner, but I encourage you to go and take a look at the paper, which has all the details, along with the detailed explanation of the algorithms and the architecture of Pacemaker. So first, let's look at what the traditional re-encoding mechanism costs. So suppose we want to convert from a K1 of N1 scheme to a K2 of N2 scheme. In this example, a 3 of 5 scheme to a 4 of 6 scheme. And say the last disk wants to transition. For every transitioning disk, for every chunk that is stored on that disk, the read, re-encode, write mechanisms needs to read all the other chunks belonging to stride, so whose chunks reside on the transitioning disk, write them to the new redundancy scheme, write the new parities, and then only delete the older stride. All in all, this costs 2 times K1 times disk capacity, where K1 is the number of data chunks in the redundancy scheme you're transitioning from. This much amount of IO is required for each disk that transitions. So now let's look at what optimizations are performed by Pacemaker. So for trickle deployed disks, remember, disks are deployed a few at a time, and so that implies that they will also require transitioning a few at a time, because only few disks will be for certain transitioning age on any given day. In order to make this transitioning efficient, instead of doing read, re-encode, and write, Pacemaker simply empties the transitioning disk onto other disks of the same redundancy scheme that the disk is transitioning from. So it doesn't require re-encoding that data. Once the disk has been emptied, and the stripes have been reconfigured, Pacemaker simply transitions an empty disk to the new redundancy scheme. Because an empty disk is being transitioned, it does not have any data and therefore no expensive re-encoding. This is apt for disks that transition a few at a time, which is trickle deployed disks. And this is at least K1 times cheaper than the traditional re-encoding approach I explained in the previous slide. For step deployments, remember that because most of or all of the disks are deployed all together, they will also require transitioning altogether. And therefore, you cannot use the logic of emptying disks onto other disks because there are no disks left to empty this data on. Instead, what Pacemaker does is that it logically transfers all the disks as they are without moving any data into the new redundancy scheme. It then reads the data and calculates the new parities, and then configures the new stripes based on the new parities, and then deletes the old metadata. This is at least N1 times cheaper and is very useful and IO efficient when most or all of the disks of a given redundancy scheme have to transition together from one scheme into another. So let's look at what happens when we combine all the optimizations that Pacemaker does to reduce transition overload. So let's look at our cluster again, which had this horrible large patches of transition overload where 100% of the IO bandwidth was spent in redundancy transitions for weeks together. Using Pacemaker's techniques, the transition overload has been brought down to well below 5% at all times. In fact, the IO efficient transitioning mechanisms reduce IO so much that the average IO required for transitioning is only 0.3% of the total cluster's IO bandwidth. And all the transitions are always safely capped under 5%. In spite of doing proactive transitions, reducing the cost, etc., Pacemaker is still able to achieve an average space savings of 14% and a peak space savings of 25%. So in the bottom graph here, it shares the same x-axis as the top graph, but it shows the different redundancy schemes that are exercised on the data stored in this cluster over time. Now, a 25% space savings for a cluster that has 350,000 disks means that 75,000 fewer disks were required because of Pacemaker. In conclusion, I'd like to say that disk adaptive redundancy suffers significantly from transition overload. Pacemaker is an IO-efficient disk adaptive redundancy orchestrator that performs redundancy transitions using very little IO. In fact, it requires less than 0.5% on average of the cluster IO bandwidth. All transition IO activity is safely capped to be under 5% at all times, and Pacemaker provides between 14 to 20% space savings on average, which translates again to tens of thousands of fewer disks. Pacemaker's design is informed by analyzing over 5.3 million disks spanning over 60 makes and models from 3 production environments across Google, NetApp, and Backblaze. Pacemaker's design is based on insights from these analyses, and there are many more insights that are available in our paper, and I highly encourage you to go and read those insights from the paper. And what I didn't have time to cover at all was that we have also developed a Pacemaker-equipped HDFS version that uses much of the HDFS's machinery to enable disk adaptive redundancy in an actual distributed storage system. The code for that has also been open sourced at this URL. Thank you for attending my talk.